All right, so we're going to pick up where we left off last time. We've been talking about recursion as a problem-solving technique. We showed how you can get rid of recursion by using memoization to avoid having to recompute values. What I wanted to do to close this off was to show you how you can use recursion to actually solve some real problems, right? Not just a Fibonacci sequence that it's just a mathematical sequence, who cares about it, right? We actually want to do something with it. And the thing that we're going to do is we're going to add up a bunch of numbers. Now, you all did this in, say, Lab 7, where you started, where you had an array of numbers, right? And you needed to sum them up. Everybody in here can write a straight up for loop or while loop to do that, no problems. Right? What I want to do is I want to look at a couple of recursive strategies that can solve the same thing. We'll look at one that's known as a decrease and conquer, and then we'll look at one that is a divide and conquer, right? Because remember that one of the reasons that people like recursion is that many divide and conquer style algorithms or problem-solving approaches follow recursion. If you can't defeat a big giant army, right, what do? You divide it up into two smaller armies. And if you can't defeat that smaller army, then you divide that up, right? You try to divide the forces up until you can overwhelm them and then conquer them. That's where divide and conquer comes from, right? So I want to look first at a decrease and conquer kind of strategy. So now if you remember the way that we motivated this talk, this recursion, is how do you make a countdown without having to write a loop? Well, we wrote a recursive countdown function that went 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. When we got to 0, that was our base case where we printed blast off instead of decrementing anymore. That sounds like a loop to me. What if instead of just printing out the number, you used it as an index for an array? If you started, say, at this array, you started at index 8, or sorry, 7, because there are 8 things in here, right? And then I don't know how to count up. I don't know how to add 8 things because I don't have a loop to do it. But I know how to add one thing, and if somebody else can add these other 7 things for me, then I can take care of the rest, right? All right, well, I don't know how to add up 7 things. But I do know how to add up this one thing and these remaining 6 things. ... Inductively thinking here, what happens when you get down to the one element only? What is the sum of one thing? It's just that thing. So let's write a loop. Let's write a recursive sum function to do that for us. The return type is going to be an integer because we're going to be summing up a bunch of integers. So const int star array. Now, instead of passing in the size here, like a for loop would need to know, I need to know how big this is because I want to start at the first one and go all the way through the last one. What we're going to do is we're going to provide it an index. Just like we did with the countdown. The index is going to start at the end here, right? So if I were to call this, I would be calling sum of the array. And instead of passing in n there, I could pass in n, but I'm going to, n minus 1 actually, but I'm going to pass in 7 here. That's going to be my starting index. And I'm going to count down 7, 6, 5, 4, 3, 2, 1, 0. And as I'm going along, I'm going to be making recursive calls on a smaller and smaller and smaller array until I get down to an array of size 1. If the index hits 0, then I'm going to blast off. Right? Now, instead of printing blast off, what am I going to do? The sum of one thing at array of index is just equal to that one thing, right? That's my base case right there. Else, right? Now index is greater than 0. So what I'm going to do is I don't know how to add up arrays of 0 through arrays of index, right? So instead what I'm going to say is, oh, okay, well, I'll let somebody else handle the sum of array 0 through array index minus 1, right? And then I'll simply just add that, right? If somebody else can do this part for me, right? This part right here. Well, if you gave me that answer and it was x, then I can just go ahead and go x plus arrays of index and return that value. So I have something to do that for me. It's called the sum function on the same array but index minus 1. Remember, I'm counting down 7, 6, 5, 4, 3, 2, 1, 0. Right? And I'll return that value right there. There is my first recursive approach to summing up a bunch of numbers in an array. GCC demo, let's make sure that it works. I made sure that there are numbers 1 through 8. So if you know Gauss's formula, it would be 8 times 9 divided by 2, which is going to be 36. Right? GCC demo.c and a.o. Hey, I got it. 36. Right? That's how you design test cases, right? You design the input and the output so you know what the outcome should be, right? And so I just put in 1, 2, 3, 4, 5, 6, 7, 8, 8 because I knew, oh, Gauss's formula, I can go ahead and compute that really quick in my head here. Right? I could have put in all 1s, and if I put in 8 of them, then I know that the outcome should be 8, right? When you design hard-coded static test cases like this is exactly what you do, right? Or you put down the input, you randomly generate it or something, then you take out your calculator and make sure that that's what you're looking for. For the second strategy here, a divide and conquer strategy, let's take a look at a picture here. If you had this on a piece of paper like I do here, electronic paper here, how would you go about doing this? Right? Would you go 1 plus 4? Okay, that's 5. Right? 5 plus 5? Okay, that's 10. Right? Or the 5 plus 12? Okay, 2? Okay, that's 12. Right? That's basically what that other strategy is doing, or what a for loop would be doing. That's not typically how I do it. Right? The intuition here that you should have is, I don't know how to add 8 things in my head all at once. I'm going to break it down. I'm going to divide it and then conquer it. Just add, oops, that's not what I want, undo, and then they changed the interface on me. Where's my undo now? There, that's it. I think that's it. Yeah, there's my undo. Blah, blah, blah. Yep, okay, good. I've got it now. They put it on the other side of the interface with their, this is GoodNotes, if anybody's wondering. GoodNotes 5, I think, and then they upgraded it. Anyway, the way that I would do this is a tournament style. 1 and 4. I can add 2 numbers in my head. Anybody can do that, right? That's 5. That's 7. That's 10. That's 14. Right? And then you repeat that process. 5 and 7. Okay, that's 12. 10 and 14. That's 24. Right? And then that's 36. Right? This is how I would typically do it. And why do I call it a tournament style? Well, everybody, it's way too early for March Madness, but everybody sees those big giant brackets, right? Where everybody starts out with just two teams in a game. There's only one winner from that game. That winner goes on to play the winner over here, right? It's an elimination tournament. The same idea here with divide and conquer. I don't know how to add all 8 numbers together. So what I'm going to do is I'm going to break it up. I'm going to break it up into 2 arrays. Right? And then I'll deal with this array later. I'm going to deal with this array right now. I still don't know how to do that. So I'm going to break it up into 2 smaller arrays. 1, 4, there's where I am right now. I can add 2 numbers. There's my base case, or similar to my base case. Right? So how do we go about doing this in a piece of code? Well, the first thing I'm going to do is name this something else. Sum A, the approach A, and then let's do sum B here. Int sum B. Right. Const int star array. Right. And then whatever else we need here. Okay. I'm also going to call there. I'll leave that there for a second. Let's go ahead and call sum B here. We're going to expect the same exact answer, hopefully, right? And then I don't know what I'm passing in here yet. Right. All right. How do we emulate that divide and conquer strategy within code? Let's come over here and think about this inductively. Let's think about this more generally. There. That was math homework help. Okay. Anyway, so let's suppose that we have this big giant array. Okay. I want to think about this more generally. Now, normally, if I looked at the entire array, it would be indices 0 through n. That's looking at the entire array. I don't want to do that. I want to look at this from the perspective of, come on, get rid of that, get rid of that. Some intermediate step in the algorithm. You've broken this array down into some smaller part. Let's look at it from the perspective that we have a left index and a right index. Certainly, if we're looking at the entire array, this would be equal to 0, and this would be equal to n minus 1. But I don't want to do that. I want to keep it general and generic. Suppose we have a left index and a right index. Now, what I want to do is I want to break that up into 2 pieces so that I have one piece over here, the left part, and another piece over here, the right part, right? And then what I'll do is I'll give that off to, oh wow, they do have a lot of upgrades. I have not used this in a while. I use this extensively towards the end of the semester, and then of course in computer science too. But wow, they've got, I don't know, what did it do there?
That basically is telling you that you misspelled left.
No, I didn't.
Yeah, that's like a
Left.
like detection thing.
Right. Oh, whatever. All right. Now I can't get it to do it again. I don't know what I did to get it to the beginning in the first place.
Yeah, that's something to do with the key. So yeah, if you do like left R, I think it'll pull it up with the red dots, and if you tap on it, I think you can like autocorrect it back to the T. So that
I'll play with it later. That's great.
Yeah.
All right. Anyway, what I want to do is I want to break this up. How do I get an index here, right in the middle? Oops. So that I can go from left up to, say, this index, M, and then M plus 1 up to R. In other words, cutting it right in half. How can I get this index right here? Through math. R divided by 2. All right. That'll work if it's, say, n minus 1 divided by 2. Certainly that'll give me something that looks like, say, n divided by 2. Right? But let's look at this more generally. What if I were somewhere completely different in the array, like 7 and 10? Right? 7, 8, 9, 10, 11. Let's go 11. Right? 8, 9, 10. I want this guy here. Is 11 divided by 2 going to give me that? That's going to give me something over here. Right? So if I've got, this is my left and this is my right. How do I get 9 out of that? Nine is halfway between two things. If I look at a number line and I've got two values here, x1 and x2, what do we call the thing right in the middle? The midway point? Statistically, what is that called? The average. Right? So how do you get the average of left and right? Left plus right divided by 2. Right? It's just the average of two numbers. Right? So let's do that over here in code. Right? First of all, let's think about a base case. Okay. Visually over here, what if it was just one value? Right? What if left equals right and we've got one value here, A? Right? That's my base case. One of my base cases. Right? What is the sum of just this one guy? A. So just return it. So if left is equal to right, oh, and I guess we should put those in there now that we've got them, int left and int right. Right? If left is equal to right, then what do I return? Arrays of left, which is equal to arrays of right. You can put either one of those in there. Right? Else, I want that midway point, int m, or middle, or average, whatever. I'm just going to keep it as m. Right? Is going to be left plus right all over 2. Careful with your math. Why? Numerator should be a numerator. Right? Now think about this code-wise. Math-wise, that's correct. What's going to happen in the coding world? Truncation, right? So 5.5 becomes 5. That's correct. That's good. Why? Because has anybody ever heard of an index called 5.5? No. So I want truncation there. That truncation is a good thing here. In fact, it's quite it's relied on all the time. Now, don't ever do that in any real code. This is susceptible to overflow. In fact, there was a bug in Java that went undetected for 15 years because of this almost exact line of code right here. And it only ever manifested when you had very, very large arrays of billions of elements. And then this would overflow because you'd go left plus right. 2 billion plus 2 billion is 4 billion. Guess what? Now you have a negative index. Doesn't matter if you divide it by 2, you still have a negative index. Have you ever heard of a negative index in this language? No. So The real way to do this is left plus right minus left divided by 2. Something like that, divided by 2. It comes out, mathematically, it comes out to be exactly the same thing. But because you're in a computer and you want to avoid overflow, this is much safer. I don't care about that right now. Right? This is just a demonstration. Right? All right, so I've got that middle index. I want to compute the sum on the left part. Go back. I want to compute the sum on the left part, and I want to compute the sum on the right part. That means I'm going to make a recursive call on the left index, up to the m index, and then I'm going to make another separate recursive call for m plus 1 through r. Why do I go plus 1 right here? Do you want to count the mth one twice? No. This is a sum. Right? So the left, int, left value, left total is going to be equal to sum of b, of the array, left up to m. And the right total is going to be equal to sum of b, or sum b of array of m plus 1, right. Now what should I return? The sum of the left plus the sum of the right. Left total plus right total. Now I did that in steps as a demonstration. I would probably not write it like this. Instead, I would write it like just a return statement. Return this one plus this one. And be done with it, right? You don't need 3 lines of code when 1 line of code will do. I'll go ahead and leave it in there for the person that wants to really, go step by step or something. Okay? Let's make sure that this works. Now remember, recursion is kind of a replacement for a loop. With a loop, you have 3 parts: the initialization, the continuation or the termination, and then your progress towards that termination. The termination condition here is this base case. All right? The continuation is me taking this and dividing it into 2 parts. If I never divided it into 2 parts, right? It was just the array over and over and over and over again. I would never make progress towards my terminating condition. I need to make it smaller and smaller and smaller. The initialization happens up here. Where do you get things kicked off in your recursion? Well, I want to compute everything from, or the sum total of everything from index 0 up to index, in this case, 7. Or, because I put it into a variable, n minus 1. Let's see if that works. There we go. GCC. I should get the exact same answer, and I do. Let's make it robust, because the way that I presented this, I intentionally put 8 elements in there. Why? Half of 8 is still even. Half of 4 is still even, right? So it's really nice, nice slicing there. But what if I had 9 things there? 10, right? Now it should be, well, I need to update this, up to 9 and n minus 1. So adding 10 to 36 would be 46. GCC. Right? All right, it still works. Right? Great, because I wrote the code like this to begin with, wrote it soundly to begin with. But visually, what does it look like? All right, so there's my original. What if I had another 9 hanging out over here? Right? You have to split ties somehow, right? You're not going to be able to split it evenly if it's not even. If there are 9 elements, 4 have got to go over here, 5 have got to go over here. That's why we rely on integer truncation, right? If I had 9 elements, 9 divided by 2 is going to be 4.5 elements. Well, integer truncation says 5 elements go over here, 4 elements go over there. Right? It's not that big of a deal. At the end of the day, which is best? Right? So there's the first approach. There's the second approach. Here's sum c, const int star array, int size. Int total is equal to 0. For int I equals 0, I is less than size, I plus plus, right? Total plus equals array sub 0. Now, this is definitely probably preferable to everybody in here because that's how you learned it, right? And that's familiar, right? You're comfortable with that, right? If you started out with recursion, and there are people who think you should start with recursion, right? Start with functional programming languages. I am definitely not one of them, right? then you would have done this or this. Right? Which one? So vote. A, B, C. All right, so yeah, it bears out, at least for those who care enough to vote. Right? Everybody else is an abstain. Right? So I would agree. Why do you need recursion here? Well, again, it's because of these subjective things. Right? The good. Right? It's a divide and conquer strategy. Right? It can help, and I like recursion in the fact that it can help you think about a problem and solve it pretty quickly. But in the end, when you go to implement it, you're probably going to want memoization, or you're going to want to take that recursion and reinterpret it and translate it to something that's not recursive. Right? It's a good way to think inductively if you have a mathematically oriented mind. Right? If you think inductively and you want to think about, oh, okay, I don't know how to do that, but I do know how to break it apart into two parts and then combine those parts later on, right? Then it's pretty straightforward to a way of doing things, right? But at the end of the day, you still have all of these objective risks that you're just abusing the call stack to do this. Just write a for loop, right? In fact, even the example right here, this Fibonacci sequence, you can take out your math book and look up linear homogeneous recurrence relations of degree 2, and there is a plug and chug way of solving it so that you get this closed form solution. All you need is like a function, right? One function call. Another way that you could do this is iteratively. You don't need to keep track of every single value. You only need to keep track of the previous two. That only sounds like two variables to me: current and previous. Then a temporary variable to add these together and put it into the temporary variable, and then move these off. You don't need this one anymore. Throw it away. Move this one to this one, and then move this one into this one. Right? I just did that with my fingers. Right? You can rewrite it as an iterative algorithm. Right? But it is helpful to start thinking about problem solving in a divide and conquer kind of approach. Right? In fact, I would recommend, if I always get at people asking, where can I get more practice? Where can I get more practice? And yet again, I will point out that you have Advent of Code, right? And it's starting in, 20 days? 20 days it's starting. But you could always go back and look at other events here, going back to 2015. Wow, has it been that long? 4, 5, 6, 7, 8, 9. Okay, it's the 9th anniversary. They got to do something special next year. But anyway, a lot of these problems are mathematically oriented and have a nice recursive solution, but they're set up in a way that if you do the recursive solution, you will be here for the next 4,000 years. Right? Instead, you need to use memoization or some other iterative approach. Right? If you're looking for more mathematically oriented stuff, another one would be Project Euler. Right? And you'd have to join to actually get the problems. It's free. It's a free account. It's a lot of math problems that are solvable by a computer program. So if you're bored, or if you get bored over the break, we now have long breaks because of the pre-session. But if you get bored over the break and you want to brush up on your C, or you want to pick up Python, like the other sections, or you want to prepare yourself for computer science 2 and take on Java, right? Then these are nice little programs that you can write and run. Towards the end, in fact, in the dead week, when you have your opportunity to resubmit your one hack and one lab, we'll probably be done with the main content of the course, and the review will take place of me live streaming these solutions. Right? There's always a competition to get to the leaderboards. Look, there was some new. Oh yeah, there we go. It's new this year. Please don't use AI to get on the global leaderboard. Right? There's no way that they can tell you whether or not you're cheating. Some people are so fast that you can barely tell whether or not they're cheating, in the past at least. Right? So those are two options for checking out other solutions that may have or problems that may have a recursive solution to them. Right? Questions? No? Well, then let's think about recursion as a segue into the next topic here, right? So let's take that same array. I forget what the values were, 8, 4, 7, 3, 42, 9, and 8. I'll repeat it. Here's another problem, one that you've already solved, right? In fact, let's see. I'll have this problem statement right here. I should have done this even before I wrote all that stuff down. All right, oops, come on. So write a function to search a collection for a particular element. Sometimes we'll use the terms needle and haystack, right? Why? Because it's as difficult as searching for a needle in a haystack, right? The needle is the thing that you're trying to search for, and then the haystack is your collection of stuff that you're searching in, okay? Sometimes we refer to them as the collection is a collection, and then a particular element, you find that key element, the key that unlocks the door, okay? You've all done this before, right? You did this in hack 7, contains within. But notice how I phrase the question here, or phrase the problem. Write a function to search a collection. What does collection mean? Stuff, right? So it would say not what? Not one thing, okay. In the context of C, how would we interpret it? What's the thing that holds stuff? Arrays, right? So we would replace that with, let me rewrite this, right? As bullet point, there we go. So in other words, C, what do we mean there? We mean to search an array for a particular element. Well, okay. Your hack 7, you are searching an integer array. Is it always going to be an integer array? No, it could be a double array, it could be a string array, it could be a pixel array, right? You're searching for that one clear pixel in the entire image or something, right? So what does that mean for a particular element, i.e. particular integer? Right? In other words, if I went with this more general statement up here, I wouldn't even begin to be able to solve the problem in a programming language, right? But if I use language-specific terminology and I get really specific, then it should be easy, okay? How could I do it with this approach? With this, I'll call it search A. Right. And now what we're going to do is we're going to return true. That's another question. What do we return? Right. Here's my search approach A. I don't know. No, I'll keep that index. Right. So if I get down to the last element here. Oh, and what else do I need? Sorry, I should have done this like this. Int key. Right. So if the first element, last that I've searched, is equal to the key, right? So if we're down at the last index and the array sub index is equal to the key, then I'll go ahead and return what? How do we want to interpret this, first of all? What in hack 7, what did you do? Contains or contains within. What did you return? You returned an integer indicating what? True, it contains it. False, it don't contain it. Right? Is that the only way that we could have approached this? No. In fact, if we had this kind of approach right here, int search C, right? How would you interpret it now? I don't have a total here. Instead, what I'll do is I'll iterate through each one of these, and if array sub I is equal to the key, so I need a key, int key, right? Then what should I return? I could return true. I'm using that as a placeholder right now. And if I never find it, I've searched through everything, I'll return false. Right? I could do that. In fact, I could change this to a bool and then use the standard Boolean library to do this. What's even more helpful, though? Okay. And the index that I'm at right now is I, right? So let's document that. Normally it would go on the prototype, but I'll go ahead and put it here. So searches through the given integer array of the given size, right? And returns the index at which it finds an integer equal to the key, the provided key. All right? Cool. Just a problem though. What happens if we don't find it? That's called an unsuccessful search. Could I return 0? Nope, false. I did not find it. How would that be interpreted? You found it at index 0. Right? That's not the case though. So when we did memoization, we used a flag value that we knew was not a Fibonacci number in order to indicate we did not find it. What is a flag value to indicate this is definitely not a valid index? Oh, we could return null, but that means that we would be returning a pointer to where we found it. Right? So I heard also -1. I like that. Right? Nobody is going to misinterpret a negative index value as a valid index value, at least in C. If you go to a programming language like Python, you can do whatever you want. There are negative index values, right? If you've got 5 things, 0, 1, 2, 3, 4, if you have to go with -1, where does it go? Back around to the other side. Right? So you can do little tricks, right? But tricks are for kids, don't do it. Right? All right, so that's a nice implementation there. There was another thing that was bothering me though. Searches through the given integer array of the given size and returns the index at which it finds it. Well, what about this example right here? What if I were to search for 8? How many of the 8s do you see? 2. This code right here would return which one of those 8s? The first one. So not just the index, but the first index at which it finds an integer value equal to the provided key. Cool? Now we put that into our documentation there. All right. Okay. Then how do we do this recursively? Now that we have the understanding that I'm going to return an index value, right? So if I get down to the end and that's the thing that I'm looking for, then what do I return? 0. Okay. Else if let's see. Actually, yeah, we could do it like this. I would actually do it a little bit different if I started over, but let's go ahead and do it this way. Else if the array of index is equal to the key, the thing that we're searching for, then I will return index because I successfully found it. Okay? Actually, sorry, go back here. Index is 0 and that's what I found. I will return 0. Okay, yeah, we'll come back. All right? Else, right? So you didn't find it at the current index. The countdown, remember? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I didn't find it at 4. So I need to search in 3. I didn't find it at 3. I need to search in 2. I didn't find it there. I need to search. I need to search. So what do? I'll return search of A, of array, and then index -1, and then the key doesn't change. You're still searching for the same key. Okay? Now, at this point, I'm going to rewrite this entirely. Right? Because I don't see any unsuccessful search here at all, right? What happens if you get down to index 0 and it's not equal to the thing that you're looking for? In other words, I'm searching for 101 in this array right here. Right? I need to return -1, right? But I don't see anywhere where I'm returning -1. So think of another base case here. If you start at the end of the array and you count down 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, what's next? If index is less than 0, that means that you've gone past the array. Don't look at anything in the array, because then that would be a segmentation fault. Return instead -1. All right. Now I can rewrite this a little bit cleaner. Else if actually I don't need this at all anymore, right? I can roll those two into the same one. Right? Because if index is 0, it doesn't matter if it's 0 or non-0. I'm still checking for the key. If that's equal to my key, I will return index here. Otherwise, I need to recurse. Let's see if it works. Let's say my key is going to be 8, right? And what did I call that? Search A? Search A. Oh, did I call the other one A? I called the other one C. Okay. So, int index of key is equal to search of A, array, and what are my parameters? Search A, the index, and then the key. So where do I start my index? At n-1, and then the key that I'm searching for is the key. There. Printf. Found %d at index %d and the line. I'm looking for key and the index of key. Okay. Ara. Where did I do ara? 51. Yeah, where? There we go. Okay. All right. Found 8 at index 7. Right. Now remember that other one where we just had a for loop that started over here. Right. We said that we would find that first 8 right here, but this recursive solution starts at the other end, right? And so it finds it over here. Maybe we want to put that in our documentation. Maybe we actually want to write some documentation, right? But it's still successful, right? Why? Because it's right there, right? Okay. How might we do this version of it then? So let's change this over to search B. I'm going to give you the array. I'm going to give you the left index and the right index, and I'm going to split it up, right? First of all, if we get down to one element, right, what do? We check to see if that's the element we're looking for. And array, so left, is equal to the key. Oh, I also need a key, right? So int key. Then I will return what? Where did I find it? At the left index. Okay. But now I need a base case, because don't forget, we need a base case where it was an unsuccessful search. Now think about your left and your right index. They're moving towards each other. When they meet, that's when you check on line 72. Right? Is that the thing that you're looking for? What happens if we go one more and the fingers cross? If left is greater than right, then we're searching an empty array. Do you remember your contains function? What happens if it doesn't contain it? What did you return? False, right? In this case, we'll return our flag value. Return -1. Or your error handling for the contains function, right? What if we gave you I and j, it contains within I and j, but I and j were out of order, right? You can't possibly search an array that doesn't have anything in it. So we'll return, nope, does not exist. Right? And now I'll make this into an else if. Right? All right, so I've got my error base case here, or unsuccessful search base case. I've got my base case where I meet in the middle. Otherwise, what I need to do is I need to compute m. And then I need to search the left. Right? So int left result is equal to a search of B. Search B, excuse me. There we go. And I'll just reuse that code right there. And int right result is equal to search of B. And I'll reuse that code right there. But it's not a sum anymore. So if I find it in the left or if I find it in the right, who wins, right? For example, here, if I were to split this up, right, oops, let's permanently do that. If I were to split this up, then both of these things are going to find an 8 eventually. Who should win? Should we report the left or should we report the right? And does it matter? Probably doesn't matter here. So if the left result is greater than or equal to 0, or greater than -1, right? Then that means that we found it in the left result. Return left result. Right? Else, now we need to search the right. So if we find it, if we don't find it, regardless, go ahead and return right result. There. Which one gets preferred then according to this code? If you find it in the left first, that's the one that gets preferred. If you find it in the right afterwards, then you find it there. Okay? Let's go ahead and run this again. Index of key, search, did I call it B? I think. And then my left index and my right index, so 0 through n minus 1, right? And, oh, I said 8, but, oh no, I'm searching for 8, excuse me. GCC. No, what did I call it? Search B. Array, left, right, key. Oh, sorry. Left, M, key. I need to give it the key too, right? correct. Not right, left, but correct. There we go. I guess I should probably print it out if I find it. Oh no, I am. Okay. So let's see which one gets preferred now. Segmentation fault. All right. What tool should I bring out of my arsenal here to find out what happened? The first tool. Valgrind. Let's find out. Demo.c. Oops. Valgrind. A.out. This will at least tell us what line it's seg faulted on, right? Core dump at line 11. That's our printf line 33. Oh, that's not going to be helpful. Oh, no, sorry. 94 is us. 94. Where are you? Oh, darn. We're getting a seg fault right there. Did I screw something up? Fine. Go away. For now. Alright. CCC. A.out. Nope, still a segmentation fault, so let's run through Valgrind here. Where are we? Oh, good. Stack Overflow. What does that tell you? We've got an infinite recursion. Right? So at this point, let's go ahead and pull out another tool, GDB, A.out, and let's run it. Layout. How do I show my source code? src. All right. And let's go ahead and break at main. Right. And give myself some more room there. All right. And let's run. All right. Yeah. Next. There are 9 things there, right? Yeah, that's correct. Searching for the key 8. Now, if I just go next, it's going to step right over this, and it's going to result in the segmentation fault because of Stack Overflow. So I will step into the function s. Right? Print left, print right. Right. That looks right because that looks correct because 0 through 8. There are 9 things in there. That's not going to be true, so we go to the next one. That's not going to be true because left is not equal to right. Right? M is going to end up being, right, refresh, 4. Why? Because 8 plus 0 divided by 2, we're good here. Right? Next. Oh, actually, step into that, right? Step. All right. Next. Now we're going to step into that. In fact, maybe I should just put my my breakpoint at search B. Break at search B. Actually, I've already done it, so just go with this. Print left, print right. All right, so 0 and 2. Next. They're not equal. Next. 0 plus 2 divided by 2 is going to be 1. Next. Refresh. All right. So step into that. What should I have now? 0 to 1. All right. So print left and print right. Okay. Step. 0 plus 1 divided by 2 is going to be 0. Right. Step, or next. Step, print left, print right. Okay. So that's going to be true now. But is print array of left, that's equal to 1. And what's my key? 8. Okay. So that's not going to be true because the key is not equal to the thing that we're searching for here. There we go. And left plus right is equal to 0, right? Print left and right. Print right. Right. Divided by 2. Okay. So that's going to be left and then is with 0 and 0. Step. Print left. Print right. And I see my error now. Am I making any progress when I finally meet in the middle here? Nope. So let's quit out of this. Yes. All right. I think I was making the same mistake as before. Right? That left is equal to right. Return. We could take care of this with one more case. If left is equal to right and array of left is not equal to the key, then we can return -1. I mean, that's an alternative, and then we don't need this base case. I'll keep it in there. But there's a better way of writing this, I'm sure. Anyway, GCC. There we go. All right. Found 8 at index 7. Was that correct? 0, 1, 2, 3, 4, 5, 6, 7. Okay. What happens if we search for 42? Okay. Found it at index -1, right? What happens if we search for, I don't know, 1? Oops. All right, found it at index 0. What else should I test here? I've tested something that doesn't exist. I've tested something that is roughly in the middle somewhere. I've tested something that's on one extreme end. Let's test the other extreme end. Right? GCC and A dot out. We should find that at index 8. Right? Let's do one more here. 2. GCC and run it. All right, was that correct? 0, 1, 2, 3. I like it. Right? So that's another way that you can use recursion here. When we come back on Monday, we're done with recursion, right? Which one of these is best among these search methods or functions that we've written so far, right? Where is it? There. Why? Because it's straightforward, right? But the thing is, what if you want to, so this is my search. This is what's going to win out. That's my search, okay? But what happens when you want to search for an array of doubles? Let's cut and paste this code, and you tell me, what would the difference be for doubles? Well, what would your array now be? Double. What would your key now be? Double. Does anything else change? Nope. Okay. Search for strings. Right. What would that be? Char, and then since it was an array of strings, it would be star star. And what would be your key? Char star. Right. What else would change? Can you use equals equals on strings? No. But you can use this thing called strcmp. If that is equal to that, then this should return a 0. So in other words, the only thing that I'm changing as I cut and paste, cut and paste, cut and paste is the type and this criteria right here. Because what if you were doing this for, I don't know, airplanes right now, right? So this would be, instead of char, it'd be airport, sorry. No, you're not searching airplanes. Airport, and then, what goes here now? Right? And that's what we're going to start talking about on Monday. What goes there is a comparator. Comparator. Right? In other words, I don't want to have to write function, cut, paste, cut, paste, cut, paste, cut, paste to do the exact same thing over and over and over again for different types. Instead, what I want is one function to rule them all. All I need to do is provide this one component. Here's an integer, here's an integer. Are they the same? Here's an airport, here's another airport. Are they the same? Here's a double, here's a double. Are they the same? Or, in the case of a string, guess what? It's already built into the language. Right? This comparator pattern. Here are two things. It returns something negative, positive, or 0, depending on the relative ordering of your stuff. Once we have this one thing squared away, we do not write our own stuff. This will all get deleted because it's already built into the language. Right? We have, this is called linear search. We have linear search, we have sorting functions, we have everything available to us. We're just going to have to reuse it. All we need is this one component right here. How do you compare these two things? Whether or not those things are integers, doubles, strings, or airports. Okay? That's where we'll pick it up on Monday. Remember, next week there is nothing on Friday, and then you still have your lab and your hack next week, but during the Thanksgiving week, there's nothing at all. Right? We don't have class next Friday, not because I want to blow it off or anything, but because I've got a committee meeting all day. Right? I do want to blow it off, though.